Okay, so in this video, I'm going to go over some application problems of sinusoidal functions and their derivatives. So this is section 4.4, application of sinusoidal functions and their derivatives. Let's go through a couple of application type problems here. So the first one being AC-DC circuits, so electric circuits problems, which you'll encounter in maybe some physics classes or electric circuits courses next year. A little bit of an introduction to that. So here we have a function I, capital I, which we usually denote as the current. And so we can express that here in mathematics too, but you'll see that symbol for capital I for current in physics classes and engineering classes as well. And the thing about current, when you're talking about alternating current, that follows a sinusoidal wave pattern. It's alternating, right? So, you're going up and down, up and down, up and down. So a sinusoidal waveform is a great model for that. Okay, and so here we're using a cosine function, 60 cosine t plus 25. T is in time, so this is a function with respect to time in seconds, and I is the current in amperes at time t. Okay, so let's have a look at, can we recall how to work with trig functions, and can we identify the characteristics such as period, frequency, and amplitude? Okay, so you might remember when we were transforming trig functions back in advanced functions, the form of a trig function would be a for the amplitude times sine or maybe even cosine of your frequency k times round bracket t minus your phase shift d, and then you have a plus c outside for your vertical shift up and down. Okay, so if you were to map the given function here as I of t is given to us, I would write this as 60 times cosine of t, and then you have a plus 25. So what lines up here? A is 60, that's your amplitude. C is 25, that's kind of your vertical shift up and down, but we're not really looking for that here. But we also, so the one thing we're looking for is the frequency, which we don't have an explicit number here. It's just cosine of t. So really what that is the invisible 1 times t. Okay, so k would be our, k would be 1. Okay, so we can write this down here. Amplitude equals 60. Okay, 60 amperes, 60A, use that for amps. Okay, period and frequency are related to each other. So if you recall, period is just 2 pi. If we are working in radians, in which we are, we'll be working with radians, 2 pi over k. All right, and if we know k is equal to 1, that's our frequency. And then our period would then be 2 pi over k. So period, we use capital T for period usually, and so that would be 2 pi over 1, which is just 2 pi, and that's in seconds. Okay. Okay, so let's look at part B now. Find the maximum minimum currents and the times at which they occur. So recall for maximums and minimums, we've been doing this over and over again. We're looking at the first derivative. So where there's I prime of t equal to 0, that's where a maximum or minimum occur. Okay, so let's look at that now. I prime of t, the derivative of the function 60 cosine of t would just simply be 60 times the derivative of cosine, which is negative sine and of t, and then the plus 25 is a constant, so that derivative is just 0. And then you could just clean this up a little bit, put the negative in front, so we have negative 60 sine t. So where is the derivative equal to 0? That's what we're trying to do. 0 equals negative 60 times sine t. Solve for t. So the nice thing about this is that if I divide both sides by negative 60, you end up just having 0 equals sine of t. So where does the sine graph have a t value that gives you the sine of that t value equal to 0? Let's just think of a sine graph. A basic sine graph starting at the origin and making that wave. And we know a period of the standard sine graph is 2 pi, or 360 degrees, but we're using radians here, so it's 2 pi. And so it will go up to its maximum at pi by 2, 90 degrees, come back down to 0 at pi, and then to its minimum at 3 pi by 2, and then back to 0 at 2 pi. So there are 3 locations in just the first cycle. So we have 3 solutions here at least. We have t equals 0. We have we will have the derivative equal to 0. Okay, and so yeah, recall this is my graph of, well, just saying sine of t, right? So it's not, I'm just highlighting that this is sine of t. It's not the derivative is 60 times sine of t, but if we're solving for a 0, I don't, we don't care about the 60. So just looking at the solutions of this particular equation. So the solutions are t, pi, and 2 pi, and every other multiple of pi, right? 3 pi, 4 pi, dot, 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 all the way to, let's say, k pi, where k is an integer. Okay? So even including negative values of k, because the graph does continue on the left side too. Okay. Now we could say, yeah, if we're working with time, well, maybe we're going to have to put a restriction in there and say, well, you're not going to have negative values of time, so we'll just stick to the positive values of time. Okay, so these are essentially what we call the critical numbers, right? Critical points, right? Where your derivative is equal to 0. And so at each of these critical points, you are going to find a maximum or a minimum. Okay, it doesn't specify what, it just says find the maxims, mins, but we're not specifying which ones are maxes and which ones are mins. If you wanted to do that, well, you can go now to the second derivative, I double prime of t, and you take the second derivative of I of t, so it's the derivative of the first derivative, which would be negative 60 times the derivative of sine, which is cosine. Okay, so there's your second derivative, and then now you can test each of these critical numbers to see whether the second derivative is positive or negative, so that you can tell whether if it's concave down or concave up, and you would have a max or a min. Okay, so remember, cosine, what's the cosine graph? Right, the cosine graph starts at 1, goes back down from 0 to 2 pi. So do you see how we have here a max at 0, a min at pi, and a max at 2 pi, right? The slopes of the tangents are 0, which means the derivative function sine at those critical points, 0 pi and 2 pi, your y value is 0. Okay, just same thing we've been doing with the other derivatives for polynomials. It's the same thing here. Okay, let's look at another example. Pendulum swings. Okay, very classic physics type demonstration. You take a physics course, a dynamics course, a kinematics, machines course. When you learn about physics, Newtonian physics especially, a pendulum swing is a very good example to kind of talk about motion. Okay, so imagine a pendulum swinging back and forth. Then one of the major assumptions you're going to make here is that there's no air resistance, no friction in the spring hinge up here, and there's no air resistance going back and forth. So we have a nice, perfect, simple harmonic motion happening here, which means it's just going to go back and forth to the same positions on the left side and the right side in perpetuity. Okay, so if we talk about horizontal distance, you're going to have, if you have your 0 line here smack in the center, okay, the far right position, you can call that the positive direction. Okay, it'll reach a maximum horizontal position on the right, and it'll swing back and reach kind of a minimum horizontal position on the left. And if you call the left side a negative direction, you can do that too. Okay, so we'll take on positive values of h on the right, negative values of h on the left, and then and there'll be a maximum h and a minimum h being the horizontal distance. Okay, so like many things that just are repetitive, right? So anything that's repetitive like this, going back and forth, back and forth, back and forth, anything that's cyclical, okay, anything that's sinusoidal, anything that has repetitive motion, right? The Earth circling around the star, the sun, the moon going around the Earth, or the hours in a day, or the days in the week, or the months in the year, right? The years repeat over and over again. The same months repeat over and over and over again. Your heartbeat, maybe not so much that. Well, not so much that, but anything that you can measure repetitive, repeating motion. Okay, a bird flapping its wings. Okay, up and down, over and over again as it flies. Okay, all of these are candidates for using sinusoidal functions to model what you see, what you observe, and we use sine functions in mathematics to help us describe that kind of motion we see in nature. Okay, so here you have simple harmonic motion. We can use a sinusoidal function to model it, sine or cosine. You could pick either one. We're going to use a cosine here. Okay, and there are a couple of things about this. When you talk about a simple pendulum, the period of its swing, the time it takes to swing back and forth, right, from its starting position back to the other side, back to its starting position, that period can be determined by this formula, okay, that has empirically been determined. I'm not going to go through derivation of that or like where it came from. Save that for a physics book. But trust me, this is the formula we can use for that. But the one interesting thing about this is that the pendulum itself does not depend on the mass of the bob at the end of the pendulum. Okay, it only depends on the length of the string or the rope or just whatever the length of what's attaching to the bob, and the acceleration due to gravity. So if you're on Earth, we're talking about 9.8 meters per second squared. Okay, so no matter how heavy the ball, the pendulum bob, you can use a marble, steel bearing. You can even just use a little piece of a wooden circular object. Okay, whatever that, it doesn't matter what the mass of that object is. Okay, it will swing with the same period back and forth. Now you can try this at home if you like. Get a piece of string, attach a couple of different objects to it, a washer, or a ball, tennis ball, or basketball if you can. Okay, and you swing it back and forth and you'll see. Okay, making sure that you're swinging it from the same starting position. Okay, and maybe I can, if you're really interested, I can show you a great physics demo of this online. Okay, so with that in mind, that period, you don't have to memorize this formula. I'll give you this formula if it comes to it. So keep that in mind. And we can use that to determine the period of the function of the pendulum. And we can use that period to plug it into the function that will model this problem. Okay, the horizontal motion of our pendulum. And our formula is actually just missing one thing. It's just missing the variable t. So it should be 2 pi t over the period. So little t is the time, the variable time, the time variable, where's the bob located at which time, and the capital T is the period, so the length of one cycle. And that's going to be the constant. Okay, so let's proceed. What are we trying to solve for here? We're interested in trying to solve for the maximum speed of the bob, the thing at the end of the pendulum, right? That circular part at the end of the pendulum. Okay, and at what time does that reach that speed the first time? Okay, because pendulum being the cyclical nature, it will repeat that speed over and over and over again. We just want to know, when does it reach that maximum speed, at what time, the first time. Okay, so again, just to kind of think about how does a sinusoidal function model this, right? So if you start your pendulum at the very far right, you're at the very edge of how far horizontally it will be. So let's say 5 centimeters. Okay, that's the amplitude. It's going to displace 5 centimeters. You let that pendulum go. It's going to swing. It's going to reach its 0 position. Okay, and that's how that's indicated there at y equals 0. And then if you're saying left is negative, it's going to reach its leftmost position at negative 5 centimeters after 1 second. Okay, and then it will come back to its original vertical position, and then the far right position at the end of 2 seconds. So one complete cycle here is 2 seconds. Okay, and we can verify that just by calculating t equals 2 pi times the square root of the length of the pendulum is 1 meter. Okay, and then we can divide that by the acceleration due to gravity, 9.8. And that's approximately equal to 2 seconds. If you put it in the calculator, you'll get 2.01. But let's just say 2 seconds to make our calculations more simpler. All right, so let's put that value of our period into the function h of t. Okay, and we get amplitude. So the amplitude is 5 centimeters. Okay, but if we're using a length of meters, you want to keep the units consistent. So I'm going to convert that centimeters into meters. So 0.05. Okay, times the cosine of 2 pi little t over capital T, which we calculated to be 2. So 2 in the top cancels with 2 in the bottom. And so what we really have is just 0.05 times the cosine of pi t. Okay, so that's h of t. That's the horizontal distance. All right, so how do we find the maximum speed? The rate of change of the distance with respect to time. That's your speed. Okay, so speed, let's call that v of t, equals the derivative of h, the derivative of distance, the displacement, if you want to be more precise here, displacement, the derivative of displacement with respect to time. That will be your velocity or your speed. Okay, so let's take the derivative. The derivative of h of t is 0.05 times the derivative of cosine pi t, which would be negative sine of pi t. But remember that the argument inside is a function as well. It's a linear function. You have to take the derivative of pi t, which would just be pi. All right, let's clean it up a little bit. We put the negative 0.05 times pi times sine of pi t. I'm not going to multiply the 0.05 and pi. We just want to keep this like this for now. You'll see why. Okay, so this is your speed function, velocity function, speed function, h prime t. How do I find the maximum speed? Maximum speed. Well, I need the critical point. I need the critical point when v prime t is equal to 0, right? If v is your speed function, then the maximum point on your speed function can be found by setting its derivative equal to 0. Okay. So don't make a mistake of setting h prime t equal to 0, because all you're going to do is solve for t when h is a maximum, when your displacement is a maximum, your horizontal distance is a maximum or a minimum. I don't want the horizontal distance as a maximum or minimum. I want the speed as a maximum or a minimum. Okay. So v prime t, which means I need to find the second derivative of h. Okay, so let's do that. So v prime t is your second derivative of h. Okay, and that's going to be negative 0.05 times pi times the derivative of sine, which is cosine. Rewrite your argument, inside function. The inside function is a function, pi times t. The derivative of pi times t is pi. So again, we're using the chain rule. This is all chain rule. Okay, up here and over here, chain rule. Wait, maybe I forgot to mention that. It's a chain rule. That's what's happening here. Okay, cleaning this up a little bit. So negative 0.05 times pi, which is pi squared, times cosine of pi t. Okay. All right. So let's set that equal to 0. Okay. Let's solve for t to find the well, we're going to be finding critical points. Really, that's what we're trying to do here. Okay. So essentially when you're dividing both sides by negative 0.05 pi squared, that kind of disappears. You really just have 0 equals cosine of pi t. Okay, how do we solve this? I want you to think of this as cosine of what angle gives you 0. Okay, so if it helps, put a dummy variable, u. Okay, and we're going to say here u equals pi t. So I don't have to think in terms of pi t, I just think in terms of one variable. Cosine of u equals 0. What is u? Okay, so we know cosine of 90 degrees is 0, right? So that means pi by 2. U equals pi by 2. What other angle? Well, if pi by 2 is 0, right? You think of the, this is pi by 2. Cosine is 0 there. It's also going to be 0 over here. So up here and down here, 3 pi by 2. Okay, so pi by 2 and 3 pi by 2. Any others? Well, you can have multiples of that too. Okay, but we're not going to care about the multiples. We only care about when is the first time it reaches the maximum speed. Okay, so one of these two is going to be a maximum, right? The other one could be a minimum. Okay, or they could be both maximums. Well, you got to find out, right? Okay, so we have our critical, we have u, right? What's the value of t then? So if I take each of these, pi by 2, so pi by 2 equals pi t. Solving for t, we get t equals pi by 2 divided by pi, which would just be 1 over 2. Okay, so there's our first one. And if I took the second one, 3 pi by 2 equals pi t. Solving for t, we get t equals, divide the pi's cancel out, we just get 3 over 2. So the second value of t. Okay, all right, so that looks fine, right? So what's the speed? Well, let's plug these into h prime of t. So, all right, so h prime of 1/2 equals, so the function is negative 0.05 times, I kind of forgot what it is, h prime of t, negative 0.05 pi times sine of pi t. So pi times sine of pi times 1/2. Okay, all right, so I'm going to get a numerical value, so you can take your calculator out, make sure your calculator is in radians if you're calculating this, or you can just get the exact value and then multiply by negative 0.05 times pi. Okay, so either way, it's fine. Just be careful. Make sure, just don't forget to work in radians. Okay, but sine of pi by 2, that's just 1. Okay, and then you can just do 1 times negative 0.05 times pi. Okay, and then I'm just going to convert that to a decimal. I'm going to multiply out the pi's with a 0.05. So what we get is negative 0.157, and we're in meters per second. So that's your speed. So it's negative. Okay, sure. What about 3 over 2? So h prime of 3 over 2. Negative 0.05 times pi times sine of 3 pi over 2. Okay, sine of 3 pi over 2 is negative 1. And negative times negative is positive. We're going to get positive 0.05 pi, which is positive 0.157 meters per second. Okay, and so that's a positive value. That's going to be your max speed. Okay, so the max speed occurs at 3 over 2, so at 1.5 seconds, and the speed is 15.6 centimeters per second if you want to convert that to centimeters. Okay, if you truly want to verify that that's a maximum, you take the second derivative, right? Well, the second derivative of velocity, right? So if you really want to go further in depth, take the second derivative of velocity, which would be your third derivative of h. You could, right? So the second derivative of velocity. And why? Why are we doing that? Because that second derivative velocity is your concavity test. So you could tell whether it's a maximum just based on the concavity. So if I took the second derivative of v, so that'll be negative 0.05 pi squared. Second derivative of v prime, I should say. Negative 0.05 pi squared will become pi cubed, and the cosine becomes negative sine. The negative in the front cancels that negative. You're going to get 0.05 pi cubed sine pi t. Okay, and then if you plugged in 3 over 2, what do you get? Sine of 3 pi by 2. Let me just make sure I took the right function. Yeah, cosine, negative sine. Yeah, okay. Sine of 3 pi by 2 is negative 1. So 0.05 pi cubed times sine of 3 pi by 2, which is negative 1, times a positive 0.05 times pi cubed, which is positive. So you're going to get a negative answer, which means that part of your graph opens down, concave down, which means the point at 3 over 2 is a maximum. Okay, so you got a maximum. If you are not restricted to the first instance that it is going to be a maximum, then you can adjust your answer to say t is equal to 3 over 2 plus your period, 2 seconds, times k, where times multiple of k, where k is an integer. That's, well, a positive integer. You could be more precise. But yeah, that's how you would look at doing this kind of question. So those are just a couple of application examples. Have a look at some more in the textbook. Refer to the practice problems here, listed here under 4.4. Okay, so it's a pretty short chapter. Okay, so you might spend some time doing some AP material. And the chapter 4 test will not cover the AP material. We'll save the AP material for one of our extension unit tests later on in March, April or so. All right, so that ends this video, and see you next class.